In this video, we're going to look at the high energy compounds that are involved in metabolism. First, we're going to just start with the whole concept of energy again. So, when we break down molecules like we do in metabolism, we get a ton of energy. So, here is the chemical reaction for breaking down one molecule of glucose, and you get negative 2,850 kilojoules per mole. Here is the reaction for a lipid, and you get roughly 3 to 4 times the amount of energy you do from sugar. Now, when we break down these molecules in the body, we want to capture this energy somehow. And we do this by having metabolism done in steps. And since metabolism is done in steps, we can capture this energy by making high energy intermediates such as ATP, NADH, etc., etc. These intermediates can then be used by the cell as a certain type of cash or currency to pay for any energy consuming processes that the cell needs to do. Now, to look at these compounds, we're first going to start with ATP. ATP is found in all organisms and is made out of adenosine, and ATP has 3 phosphates. ADP has 2, AMP has 1. The bond that connects these phosphates are phospho and hydride bonds, and connecting the phosphate to the adenosine is your phosphoester bond. Now, the way you get energy from ATP is by transferring a phosphate. You can either transfer 1 phosphate or 2 phosphates at once. Now, in ATP, when you use ATP, you just don't break off a phosphate and magically get energy. That's not usually how it works. What happens is that you take this phosphate and you transfer it onto another molecule. And by transferring to another molecule, this is how you get your energy. Now we can see we have a list of multiple different phosphate compounds. These energies are the energy you get out by removing a phosphate. You can see that in your body, ATP is actually not the highest molecule. There are 2 above it, your pyruvates. Now these values, these negative delta G values, are called phosphoryl group transfer, not proteins, but values. And note that all these molecules, they're kinetically stable. Even though delta G is very negative, you just don't randomly lose your phosphates. In fact, that would be horrible if you just lost these phosphates. You need an enzyme to move around these phosphates. So before we move forward, let's actually take a look at why ATP is such a high energy molecule. And there's roughly 3 factors for it. So we're looking at the phosphates of ATP here, and we're looking at before breaking up the phosphate and after breaking up the phosphate. So first off, we have resonance structure. You can see that this oxygen connecting the 2 phosphates, you can have a resonance structure in which you have a double bond here, which will mean this oxygen's negative, or a double bond here, which means this oxygen's negative. If you remember from organic chemistry and general chemistry, oxygen is an electronegative atom, so it wants to be negative if it can. So in this, you only have 1 oxygen that can be negative at a time. Compare that to the form that is broken up. Now, each oxygen from your phosphate can become negative. You have better resonance structures here. So that's one reason why cutting this phosphate is lower energy than having them connected. Another reason is that you have a bunch of negative charges all together. These negative charges will want to repel each other. Well, when you break your phosphate, you don't have many negative charges next to each other anymore, so you don't have as big as a repulsion. So that also makes this more energetically favorable to cut it. And lastly is solvation energy. Excuse me. So in this form, where you have your phosphate connected, water water cannot surround your molecule as well as it can in the separated form. So water has better interactions when your phosphates are separated. You're forming more hydrogen bonds than it does when it's connected. So that means you get more energy out if your phosphates are not connected. So these are the 3 reasons why you get energy from breaking a phosphate bond. Now, how do we use this energy? Well, these high energy compounds are connected to endergonic processes to make non-spontaneous processes spontaneous. So we're going to look at an example reaction here. We have A plus B going to C plus D, has a certain free energy, and D plus E going to F plus G, has a certain free energy. If delta G is a positive value, reaction 1 won't happen. However, if delta G2 is a big negative number, such as when you combine G1 and G2 together, this is a negative number, now reaction 1 will happen. And you notice that they are connected because they both use D. D as a product in our first reaction, D as a reactant in our second reaction. And the logic is this. If delta G2 is super negative, this D plus E is going to be converted. It's going to want to keep doing this, and the only way to get D is from the first reaction. So all the D from the first reaction will be used by the second reaction. Therefore, you're going to keep making D in the first reaction. You're going to keep using A and B, even though the first reaction isn't spontaneous on its own. Reaction 2 is pulling D from reaction 1. And to make D, you need to get A and B. So you could actually combine these reactions. You could say A plus B plus E makes C plus F plus G. Notice that since D is made and created, it's actually not part of your final reaction. And this delta G, which is G1 plus G2, we call that G3. And this is actually a topic we covered in Gen Chem. And this whole idea, the way it relates to metabolism, is that we have a bunch of coupled reactions. We have multiple coupled reactions. Some of them are not favorable. Some of them are favorable. But the big thing is, as long as the overall process or pathway has a negative delta G that is exergonic, then the whole pathway will move forward. So that's what we need to keep in mind from this. Now, we can take a look at an actual example in metabolism of this. So the first step of metabolism is to phosphorylate glucose to make glucose 6-P. This is not favorable. But breaking ATP is favorable for the reasons we talked about before. So if you take ATP, transfer that phosphate to glucose, you have an overall negative reaction. So you can have glycolysis started. Also, let's say we want to remake ATP. Well, we have phosphoenolpyruvate to make pyruvate. Very negative. ADP to phosphate, roughly 30. Notice when you're doing reverse reactions, if the delta G is negative in one direction, if you're going in reverse, it's the same number but positive. So I just want you to notice that. Anyways, back to the idea. So if we want to couple phosphoenolpyruvate with ADP, we can remake ATP because this is an overall negative reaction. So that is how we make endergonic or non-spontaneous reactions happen inside the cell. That's it for this video. See you in the next one.